Good evening and welcome everyone. Shaastra Spotlight is back bigger and better than ever with a series of exciting fireside chats, fascinating lectures, and intriguing demonstrations. We welcome you to the first lecture of the Shaastra Spotlight series on the SubX Day 1 of Shaastra 2021. We are extremely honored to have with us our very first speaker of the series, Dr. Peter Atkins. Dr. Atkins is a renowned chemist and prolific author of several chemistry textbooks. He was the professor of physical chemistry at the University of Oxford from 1965 until his retirement in 2007. He has published over 70 books, including university level textbooks and books on science for the general public worldwide. The best known of the former is his physical chemistry text, which is used throughout the world, including our own CY 1001 course at IIT Madras. Today, he will be speaking on the origins of laws of nature, and we are extremely honored to have you today with us. Thank you, sir.
Well, thank you very much indeed. It really is a great pleasure to be able to talk to you, and I really do compliment all the organisers of this series of talks. I think it's really splendid, and I think I'm very happy to give them my small support. I will share my screen with you.
Sure.
And I will I think you're seeing the correct screen now. I'm going to talk about something that concerns us all. Everyone else in the world, just the normal people in the world, look on things and see a scene like this. But scientists are rather different. They look under this scene and see that it's ruled by a number of laws. And the question arises, how do those laws come about? I once went to a lecture by an acquaintance of mine, a philosopher, not a scientist, who said, well, the simplest way of understanding...
Sorry to interrupt. We can't see your screen. Could you try presenting again?
He tried to
Yes, sir.
Is that all right?
Yes, sir. We can see it now.
Okay. I'm not sure that I can see myself now. Sorry, I need to
present it.
Can you see that screen now?
Yes, sir. We can see the screen now.
Good. Okay. Well, as I was saying, I went to a lecture by a philosopher friend of mine who said that the simplest way of understanding the laws of nature, why an electron moved in a particular direction, for example, was because God pushed it in the right direction all the time. And I thought, this sounds rather a waste of time of any God. Surely, as a scientist, there must be a simpler explanation. And so we scientists look at the world and see that it's a beautiful place, like this picture attempts to show. And But we also look underneath the, the appearances and we see an underlying simplicity. So what I would like to do is to look for the origin of the laws of nature in an extremely simple way. And I decided that I could account for all the laws of nature in 3 principles and 1 assumption. One principle was indolence, not doing anything at all, total laziness. Another principle was anarchy, allowing everything to happen, and not trying to impose any laws, and seeing whether laws emerge from anarchy. And thirdly, the third principle was that if indolence and anarchy were inadequate for accounting for all the laws of nature, then one could always resort to that useful technique, that of total ignorance, and see whether ignorance could account for laws. And what I want to do this afternoon is to try to convince you that there is that these 3 principles and 1 hypothesis accounts for everything. And the hypothesis is as follows. Here is a simplified picture of the universe, which began a long time ago at this point where there was the Big Bang, and we're at about this stage. Now, it's quite possible that we are in one of these daughter universes of a universe that emerged from another universe and so on. But I think what I want to focus on is thinking about really an initial universe, this particular universe, which was preceded by absolutely nothing. And I want you to focus on the nature of absolutely nothing and see what happens to absolutely nothing when it turns into our universe. So that is where I'm focusing. And here is a picture of absolutely nothing. And the absolutely nothing does have some properties. For example, it's totally uniform. You can't have lumps of dense nothing and then thinned out nothing. So nothing is really totally uniform. And I shall represent it like this icon. Also, it is isotropic, but if you go round any point, absolutely nothing doesn't change. There are no lumps in nothing. And thirdly, it's totally empty. You can't have things in nothing, otherwise it wouldn't be completely nothing. So here are my here is my description of what I mean by absolutely nothing. And be quite clear, I don't mean empty space. I mean absolutely nothing. No space, no time, absolutely nothing. Now, before the creation, we had absolutely nothing. And after the creation, we've got all this stuff that surrounds us at the moment. My hypothesis is that when absolutely nothing turned into the current universe, the properties of this universe inherited the properties of absolutely nothing. So immediately before the Big Bang, the universe inherited those 3 properties of absolutely nothing. It inherited uniformity, it inherited isotropy, and it inherited nothingness. So that's my hypothesis, the inheritance of the properties of absolutely nothing as soon as the universe came into existence. Bear that in mind. So with that in mind, think about the role of indolence, of laziness. And I'll start with probably the most important law in the whole of nature, which is the law of the conservation of energy. The conservation of energy is like a policeman forbidding certain changes in the universe. But it is also the basis of causality, the fact that one event can cause another. And causality is the foundation of science, and science is the foundation of understanding. So if one can understand the origin of the law of conservation of energy, then one really understands the basis of science and the basis of understanding the universe. And I'll start, well, everyone knows that energy is conserved. I mean, if you throw a ball up, then that's the way that it behaves, and the potential energy is gained as the kinetic energy is lost, and then kinetic energy is gained as potential energy is lost. The total energy is constant. Why is energy conserved? For that, I need to tell you about a very famous mathematician, Emmy Noether. Emmy Noether was alive, unfortunately not for very long, at the beginning of the 20th century, the end of the 19th century. In my view, mathematicians either die close to zero or close to infinity. And unfortunately, she was one who died close to zero. But while she was alive, she came up with an enormously important theorem. And the theorem states that whenever you have a conservation law, you have a symmetry. So if we're looking to understand the law of the conservation of energy, then we have to look for the corresponding symmetry and then account for that symmetry. And the symmetry that underlies the conservation of energy is the uniformity of time. So that if time goes tick, 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 uniformly on a cosmic scale, then by Emmy Noether's theorem, energy is conserved. If, on the other hand, energy went tick, 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 it was not uniform, like I think it seems in some lectures, then energy would not be conserved. So what we have to do is to account for the uniformity of time on a cosmic scale. Now, go back to my hypothesis. When there was absolutely nothing, there was no time, everything was uniform. When time came into existence, it inherited that uniformity of time. So if that means that energy is conserved. So we can understand why energy is conserved. We can understand causality. We can understand understanding on the basis of the inheritance of the uniformity of absolutely nothing when the universe first comes into existence. So here is the uniformity of time and the conservation of energy. Because a secondary question, of course, is where do we draw this line? How much energy is there in the universe, and where did it come from? Should we draw the line there, or should we draw the line there? I mean, we can answer that question, I think, as follows. We can estimate the total energy of the universe, and therefore know where to draw these lines. And to estimate the energy of the universe, we weigh a galaxy, take its mass, multiply its mass by c squared, and get the energy that this galaxy represents. Then we look at the entire universe, of which this is a fragment. We measure the mass of that galaxy, and we get a very large energy. We measure the energy, the mass of that one, add it to the first, that one, add it to that one to another one, and do it for every galaxy in the universe. And of course, what we then get is a colossal energy. And so philosophers and theologians wonder where this huge energy comes from. But we scientists are circumspect, and we say, is there another contribution to the energy? And we know that there is. There's the attraction, the gravitational attraction between galaxies. And when you have attraction between objects, it lowers their joint energy. So back to the universe, we had a very large energy. This galaxy attracts that one, it lowers the energy. This one attracts that one, it lowers the energy. This one attracts that one, and so on. And you can see where this leads to. I suspect that if you also include dark energy and dark matter, I think the total energy actually goes down to zero. So where do we draw that line? I think we draw it there. And so philosophers and theologians no longer need to worry about where all the energy came from. There isn't any. Before the universe was created, there was no energy. After the energy, now, after the universe was created, now, there is still no energy. But it's a much more interesting distribution into positive and negative contributions of the energy. What about the other laws of nature? Well, if space is uniform, then Noether's theorem tells us that linear momentum is conserved. And so that is another law of nature. And once again, it arises from the inheritance of the uniformity of nothing. Another law, of course, is that angular momentum is conserved. And Noether's theorem requires isotropy of space for that to be conserved. So how much angular momentum is there in the universe? Well, that can be measured because we know that galaxies rotate. Before the creation, the total angular momentum of the universe was zero because there was nothing to rotate. Now, galaxies rotate, but they rotate in different orientations at different rates, and the total angular momentum is still zero. So I like to think that when the famous thermodynamicists Joule and Kelvin were examining the equivalence of energy, of work and heat, then what they were really doing, and establishing the conservation of energy, what they were really doing is looking at the shape of space-time and seeing how the current shape was inherited from absolutely nothing. What about the role of anarchy? Well, a lot of people contributed to this, and I will focus on the Fermat's principle of least time, which tells us that effectively that light travels along a path that takes it the least time. But how does it know when it sets out that this path will be the path of least time? Suppose it made a mistake and it got to this point, realized it's made a mistake. Well, what could it do? It can't go back and this way because it will waste time that way. So how does it know which is the path of least time? I think it's because of the wave nature of light. Here's the wave structure imposed upon a path that is not straight. That path has a neighbor, and here is the wave superimposed on that path. And I've drawn the phase, excuse me, at the end of I've just shown you what the phases are, and they're quite different. Take another path, this one, and look at the phases here. And as you see, they're all different phases. And think of hundreds of millions of different paths with a random distribution of phases. They wash each other out. But think of a straight line path. It also has neighbors, but notice that the phases are very similar. Here's another one with two neighbors, and the original now. Once again, all the phases are very similar at this point. Technically, there are no first order differences. So think of all the paths here, all the light coming through these paths, allowing it to go everywhere. All the phases, all the paths have phases, all the paths have neighbors with phases that cancel at this point. And so all these different paths actually cancel. Whereas a straight line path only has neighbors that do not cancel. So in other words, by allowing light to go everywhere, we get a straight line, we get a law of nature. So anarchy results in a law. Now, of course, that applies to mechanics as well, to dynamics. Because before 1927, of course, the electron was simply a particle. But now we think of it also as a wave. And because it's a wave, it interferes just like I was showing the paths of light. And just a short reminder about quantum theory, that the amplitude of a wave tells us the probability of finding a particle in a particular region of space. So here there would be a high probability of finding the particle, a smaller probability of finding the particle, and zero probability of finding the particle. Now, with that in mind, think of the diagrams I showed before. A curved path for the electron now has waves that have phases that cancel. A straight line path has neighbors that do not cancel. So the electron travels in straight lines in the absence of fields and so on. So once again, out of this anarchy, we obtain a law. And that law can be developed, just as in classical mechanics, one talks about action, which is the amount of effort you put into the path. And you end up with Newtonian mechanics if you look for paths of least action. So in quantum mechanics, through the work of Feynman, you end up with quantum mechanics if you look for paths of least action again. And once again, we end up with Newtonian mechanics as an approximation to quantum mechanics. So by allowing anarchy, we can understand the whole of quantum mechanics. Now, it's not only quantum mechanics that we can understand, it's also electrodynamics. Think of the electron again. There it is, wave. And I'm going to tell you about modern theories of the fundamental forces, which involve gauge theories. Now, a gauge is simply a ruler, and we can apply the ruler to this wave and measure off the distances between peaks. But we can shift the phase of the wave and move the gauge, and the probability of finding the particle, the observable that we make, the observation that we make on the system, is unchanged. Notice that the amplitude of the wave remains the same. In other words, the observation of the probability of finding a particle somewhere is gauge invariant. Now, gauge invariance is very important. It means that if you looked at a small region of space, and here is an electron traveling in this direction, the electron enters through one phase and leaves through another, and there is no change in the probability of finding the particle inside this region. In other words, sorry, we go back, electric charge is conserved. So this symmetry, gauge invariance, global gauge invariance, means that charge is conserved. And that is really one of the great laws of nature. It means that since we started off from absolutely nothing, there is no starting point for this wave. We can start it off here, or we can start it off here. An electron wave traveling in that direction is gauge invariant. And that leads to the conservation of charge. And we know that there's zero charge in the universe. When there was nothing, charge was zero. Now there is positive charge and negative charge, but we know that there are equal amounts, because there were not equal amounts. So strong is the electromagnetic force that it blast the universe apart before gravity had a time to condense it into the clusters we call galaxies. But it's deeper than that. Go back to this wave. The wave, of course, satisfies Schrödinger's equation. If we shift the gauge, we move its phase, it still satisfies Schrödinger's equation. But suppose we shift the phase by different amounts. Here we shift the phase by a small amount, here by a large amount, here by an even bigger amount, here by a small amount again. That shifted wave, the yellow wave, no longer satisfies Schrödinger's equation. In order to satisfy this shifted gauge, we have to add a term to Schrödinger's equation. And the terms that we add are nothing other than the Maxwell equations. So equivalent to the Maxwell equations. So in other words, local gauge invariance, the fact that observations are independent of these local changes in gauge, results in the laws of electromagnetism. So in other words, we get Faraday and we get Maxwell and we get all the laws that govern really the modern world of electromagnetism. I see that I don't have really time to talk about ignorance. If I had, I would talk about the origin of Hooke's law, and I would talk about the origin of the gas laws, both of which are based upon ignorance. Let me go on to probably the most important law of all, which is the Boltzmann distribution. I want you to imagine Boltzmann lying in his study with empty bookshelves, throwing his books onto the shelves at random. And it's possible that he would get that distribution, but it would be very improbable. Once again, he threw them again onto the shelves and got that distribution. That's more probable, but still not very probable. He had infinite time, so he threw this on his shelves again. And this time, this is the distribution that he got most often, in trillions of times of throwing his books onto the shelves. This is the distribution that was the most probable. And he found that it fitted this exponential curve. In other words, the Boltzmann distribution emerges just from a random distribution of throwing particles onto the available energy levels. And if I was confined to a desert island, I would really want to take Boltzmann with me, not as a social companion, but as an intellectual companion, because his principle accounts for the stability of materials, and it accounts for the ability of materials to undergo change, provided the temperature is above zero. It also accounts for what we understand by the nature of the concept of temperature. It is simply the parameter that occurs in his distribution. Now I have to move on, I'm afraid. I talk more about that. Let me go back to the scene you might have seen when I'm perhaps not sharing my scene earlier. Why do things happen in this scene? Why does anything happen? What causes things to happen? What is the underlying law that drives change? Well, it's probably my favorite law of nature, which was the second law of thermodynamics. It says that really everything happens because things get worse. And we know that this does not happen. Things do not get better. We know that things tend to disperse in chaos, in disorder. So basically, everything that happens in the universe can be summarized as something getting worse. This might be energy dispersing in chaos. It might be matter dispersing in chaos. But the wonderful thing about the universe is that this dispersal does not happen in isolation. There might be a mechanism that links into this dispersal that can drive the opposite of dispersal elsewhere, provided overall everything is getting worse. There can be local changes which we perceive as the emergence of structure. So this might be a hydrocarbon fuel. It burns in a real engine. The hydrocarbon molecules disperse as carbon dioxide and water molecules, and the energy released in the combustion disperses into the surroundings. This might be the real engine that engineers have designed. This might be a pile of bricks and stones, and the dispersal here drives the emergence of structure here. Overall, the universe is becoming just more chaotic, but locally there can be the emergence of structure. Once again, this might be breakfast. This might be digestion. Well, it might be ingestion. This might be digestion and all the metabolic processes going on inside our bodies. These might be amino acids, which are turned as this dispersion occurs, a metabolism occurs in our bodies, and a structure emerges like a protein. So we can see that the second law really accounts, which is simply this portrayal of the consequences of chaotic dispersal, accounts for all change in the universe. And it really opens our eyes to seeing the fusion processes going on in the sun, dispersing energy, it being captured on Earth and being used through photosynthesis to drive the biosphere into existence, and our consumption of the biosphere leading to the growth of our organs, and in particular the growth of the organ, our brain, that enables us to stand back from all this wonderful activity and to understand it in terms of very simple processes. So summary, I think I now have come to the end of my time. I hope that you have seen that if you accept that before there was the universe, there was absolutely nothing. Now, of course, there is. But when the universe came into existence, the universe inherited what there was initially, that is, nothing at all, and the uniformity was inherited by the universe. If uniformity was not sufficient to account for the laws, anarchy, allowing everything to happen, accounted for them. And although I didn't have time really to go into it in detail, ignorance, leading, for example, to the Boltzmann distribution and the second law of thermodynamics, accounts for all change. So I think we can account for all there is, all the laws of nature, by thinking about the emergence of the universe from absolutely nothing, doing nothing, and enjoying the consequences of what didn't happen. So thank you very much indeed.
Thank you so much, sir, for that very insightful talk. We now have a few questions from the audience. Shall we start the questions? So the first question is, did your own teaching experiences and work as a tutor, lecturer, and later professor of physical chemistry in Lincoln College, Oxford, influence you to write your own textbooks, especially the college level textbooks?
Very much so. I think, there's the bigger question of enjoying science and knowing that it provides understanding and comprehension of the world around us. And through understanding and comprehension, I think you develop a deeper pleasure in being in the world. You don't have to comprehend. You don't have to comprehend music in order to enjoy it, but it deepens your delight if you do.
Yes.
And also, more specifically, the Oxford system of education is through tutorials where it's one-on-one or two-on-one for talking to one's students in intimate surroundings, really, and getting to know their difficulties, getting to know their understanding, getting to know what explanations worked and which explanations did not work. And it was through that experience that I thought, well, I can share that with the wider world. And as a result, I was led to write not only the physical chemistry text, which was a direct outcome of my teaching experience, but also the books on science for the general public, which reflected my deeper pleasure and wish to share scientific insight with the rest of humanity.
Thank you for that answer. So, along the same note, your famous book, Atkins Physical Chemistry, which is used throughout the world, is in its 11th edition, and its first edition came out in 1978. So, why does it have so many revisions, and how often do you think books, especially for college students, need to be revised?
Well, we instructors expect our students to learn the subject in one course, and we examine them and we say, you didn't understand. Ah, you did understand. We authors have the luxury of not getting it right first time. And I've had the luxury of trying to get it right 11 times so far. So I think it's a process of deepening understanding. You write down what you think was the explanation, and then you realize, or someone else points out, that it isn't correct. And so you do a new edition, which you hope conveys the truth. And each successive edition, I hope, gets closer to the truth. Also, it's not only the truth, because technology changes. And so, in the first edition, I drew all the illustrations by hand. Now, of course, I use software to do everything. Mathematical software is now a great help in helping people resolve exercises and so on. So you have to take that into account. People's expectation changes. The more people work with things on the internet, the less they're used to using a book. And so attention spans change, and the type of presentation that they're used to changes. And so new editions must accommodate changing attitudes to what people are looking at and digesting. And also, people write in to say, I think I have a better explanation than the one in the book. And so I steal that explanation, if it's a good one, and incorporate it. So it's a process of progressive refinement and improvement and adjusting to what people expect and hope for.
Okay, so that was a very nice answer. Coming to the young students who use your textbooks and science and research as a whole, attracting young students to scientific research has also become a topic of growing importance from the point of view of science. So, scientists are becoming concerned about a potential bottleneck of scientists and engineers, which could hamper the growth of high tech industries, particularly biotechnology and information technology. So, how can we interest the younger generation in both knowledge as well as science?
By showing the joy of understanding. That's the short answer. I think there is no other intellectual activity that opens our eyes to the beauties of the world than science. Of course, literature and the arts decorate our world and give us joy. And in a sense, I suppose literature can add to understanding of personal relationships and so on, and the way society operates. But to get deep understanding, true understanding of the fundamental nature of the fabric of reality, only science provides it. And having a scientific explanation doesn't detract from the pleasure of simple enjoyment, because you can turn off your deep enjoyment and your comprehension if you just want to lie back and listen to music or look at a picture or read a book. But when you want intellectual engagement, then science provides it, and that deepens joy.
Okay, sir. That was very nice. We have a few questions from the audience. So Anubhav Prakash has asked, how are we sure that there was absolutely nothing before the Big Bang?
Well, that is, of course, a deep philosophical question. First of all, you have to ask whether time is circular. We might just be testing a few billion years of time, and it seems to be moving in a straight line. But suppose it was circular, then there would be no beginning. And so the question of what there was before the creation would not arise. And we've got currently no way of telling whether time is circular. Now, if time is not circular and there was a beginning to the universe, then what could there be before there was anything except nothing? Because if there was something, then you could simply push back the question and say, well, where did that something come from? And presumably you trace it back to a sort of nothing. So this might be a very naive understanding of the fabric of reality. If time is not circular, then presumably there was a time before there was anything. And I think we need to call that absolutely nothing, but I might be wrong.
That was very interesting, sir. So, another one of our audience members, Prabhananda, has asked, if you travel back through time, what advice would you give to your younger self?
Oh, that's far too personal a question. Would I do chemistry? Yes, I would do chemistry again, is a sort of answer. I mean, the choice when I went to university or when I was in high school and had to begin to specialize, and then went on to university, was which of the sciences should I do? Should I do physics, chemistry, or biology? Um, Physics, I thought at that stage, was too mathematical for my taste. Biology was too embarrassing because I, as a young pubescent youth, was seeing all these things copulating and reproducing, which was deeply embarrassing. And so, sort of in between them, neither too mathematical, nor too embarrassing, was chemistry. And I'm glad I did it because chemistry is so central. As you see, I do think about physics a great deal, and chemistry enables me to look at that fringe of chemistry, that frontier of chemistry. And also because so many of the wonderful applications of chemistry are now in biology, it enables me to see how chemistry applies to biology. That is another frontier of chemistry. So by doing chemistry, it put me right in the center of the sciences and able to share my vision of science. So that's something I would not have changed.
Okay. Okay, sir. And one last question. Many of our audience members have actually used the famous Atkins physical chemistry for reference for their studies. And there were many queries over what area does your work currently focus on. So could you please elaborate on the same?
It focuses on writing more books. I mean, as you can imagine, writing a textbook is, it's not just one book, of course. At the moment, I'm working on 4 books simultaneously. It becomes really a full-time occupation. I I realized that a long time ago, before most of you were born. As you heard, the first edition came out in
Nice.
1978 of physical chemistry. Um, by 1980, it was clear that it was an important contribution to science worldwide, and I had to keep it alive and develop it. And that meant I could no longer give 100% attention to my research group. And it was not fair, I decided, on young minds to neglect them. And so I closed down my research activities. And ever since then, which I suppose is now 40 years, I devoted myself to full-time writing. It means one still has to keep up with what's going on in the world, but no longer do I have the responsibility of developing young research student minds. I have a great responsibility, for example, for developing the understanding of science in undergraduates and the general public. So, in a sense, one does research for that. but it's not what we really call chemistry research. It's intuition mostly. So, in other words, since I've been talking about nothing in this lecture, currently I do nothing in terms of research.
Okay, sir. Thank you so much for your contributions to the world of science. And we are extremely honored to have you with us. And thank you once again for being a part of our online lecture series. To the
Listening,
audience, thank you, sir. To the audience, please find the attendance and feedback form link on the chat and kindly to fill the same. Participants who attend 4 or more live lectures as a part of Shaastra Spotlight 2021 would get e-certificates. And next up, we will be having a lecture demonstration with Robot Thespian in Clio at 4 p.m. tomorrow and a fireside chat with Mr. Robert C. Martin at 5:30 p.m. We request you to attend all those lectures too, and we thank the audience for your patience and hope you had a wonderful time. Thank you.